Hello. Um, Oops. Okay. You should hear me. Should see the desktop. Everything seem okay? Everyone's coming in. Okay. Great. Seems like okay. Um, all right. So midterm will be available, like it says here, the midterm will be available right after class, and you have the whole rest of the day to work on it. You know, turn it in. It's got 7 problems on it, and you need to turn it in by the end of the day. Now, I'm not logged into Brightspace. If what you'll see when it becomes available is it's a PDF document, but it's also a text file. I realize that it's sometimes hard to copy and paste. Okay, what I want to do is return a PDF file to me. Now, there's a couple ways you can do that. You can download the exam, print it out, and write your answers on it and scan it back in. That's option 1. Another option is to download it and create like a Google Doc or a Word doc or anything you're familiar with. Like if you know Markdown, if you know HTML, if you know Jupyter worksheets, just like anything you want, you can you can solve the problem any way you want and then create a PDF document because Word, all those will, Google Docs, all of them can be saved as a PDF file. But to make it a little bit easier to make those, I put up a text version of the exam because copying and pasting out of PDF documents sometimes doesn't work very well. So I took all I stripped out all the formatting from the document and left it as just a plain text file. Then you can easily copy and paste into something else. Like if you want to copy and paste the problems into a Google Doc and then solve them in a Google Doc. Okay, so the main requirement is you submit to me 1 document. That is your answers. Whether it's written out on the exam like in a classroom where you scan it back in, or if you want, you can type your answers. The nicest thing would be if you could type your answers even using Word or Google Doc, or if you know how to use it, HTML, Markdown, any of those. Okay, so whatever you feel most comfortable with. Okay. Yeah, and make use of like I say, make use of if you need it, make use of the text file. That makes it easier. It makes it's real. Obviously, from a text file, you can copy and paste without any problem. I noticed that the PDF is just unreliable. You copy and paste, and the formatting can get all messed up. Okay, all right. So, anybody had a question about the exam, about the mechanics of the exam? Anybody have a question about what you have to do?
So can I just write the answers out on a piece of on the pieces of paper and scan that into a PDF?
And the trouble with that is it makes it hard. You should be able to create a better document than that. Like if you just write your answers, if you can write your answers, if you print the exam and write your answers on the exam, that makes it a lot easier for me to grade it, because then I see exactly what problem you're solving, just like I would be grading a regular exam. If you just write answers on blank sheets of paper, I found that's real hard to grade. It's real hard to figure out where one answer starts, another answer ends, and you should also be able to you should be able to produce a better document than that. Like either with Word, or something like that. But yeah, I'm kind of hoping that you don't just write answers on a blank piece of paper and scan those in, because I found in the past that those get kind of hard to read. Okay, so but the PD, like there's a plain text document. You can print out the plain text on pieces of paper and write your answer on those. Yeah. So if you're going to scan it in, you might as well scan it in after having written on well, it actually depends on whether you have a printer or not. If you don't have a printer, you don't have a way of printing things out. But whatever, if you have no way of printing it and you have no way of creating any other document, then you don't have any choice but to write your answers on blank sheets of paper and scan them in. Okay, so if that's your only option, that's your only option. So try to make that a last ditch option, but if that's your only option, then that's your only option. Okay, so
Okay, thank you.
Yeah, so one option would be just write but don't write the answers on separate pieces of paper. So if like problem 3 is on page 4, put problem 3 on a page 4, because that'll help me find the problems. Okay, so at least keep the page numbering the same. I think problem 1 and 2 are on page 1, problems 2 and 3 are on page 2, problems 3 and 4 are on page 3. So that would help me find the problems. Otherwise, it becomes a nightmare. Yeah, trying to find people's answers to a problem. Yeah, it can take me forever to grade exams if I have to like look for an answer in each document. So at least keep the page numbers the same. That'll help a lot. Okay. Well, other questions about mechanics or anything like that, about what's required? During the exam, if you have questions, you can send me an email to get clarification, especially if you think there's a misprint. Yeah, if you think if you think I might have goofed up something, send an email right away. So send emails. I have some classes this afternoon, but I'll try to answer the emails as soon as I can. Yeah, and so you have definitely you should send an email if you have a question about something. If you want clarification or if you think there might be a mistake, please send an email. Okay, so feel free to ask questions during the exam. Anything else? Let's see. Okay.
I have a question about the clipping algorithm.
Uh-huh.
So I see in the source code that it creates new vertices at z=0 and not at z=-1. Is there a particular reason for that?
I'm not sure you mean by z=0. Yeah, that's a good question. Oh, no. See, they've already been no, I did that as a little trick so that the clipped vertices were easier to find in the output than the original vertices. So that was just a little trick to make the clipped vertices stand out. Because after the clipping algorithm, the z variables never looked at anymore. Once everything's been projected, the z variable really doesn't get looked at anymore. So I had this idea that in the clipping algorithm, when I create a new variable, I'd give it a z value of 0, and then it just kind of makes the clipped vertices, which are new, stand out in the list of vertices. So yeah, that's a good point. That was and I think I thought I made a little comment in there. I can't remember, maybe I didn't, that it was just a trick to make those vertices stand out a little bit in the output. Yeah, that has no effect on the algorithms. After the projection stage, none of the algorithm steps look at the z values anymore. So you can kind of do whatever you want with the z value. So you're projecting into the z=-1 plane. So I made those z=-1, though I could have made them 0 or anything. And then I had the idea in the clipping algorithm, let me make the new vertices with the z coordinate 0, so they stick out, they show up in the output a little bit. Okay. Yeah. So that's just a little hack to try to make debugging output kind of easier to read. Mm-hmm. And that's the kind of, that's a good thing. Little details like that are good to see. I did that little trick to help me when I was doing the debugging, and it did help me with the debugging. And it's a little detail that it's worth noting, because you're right. Why is it there? I thought I commented it. I should go back and put a little note in there about why those have z=0. Okay, that's a good question. Okay, what about now? What about the review problems? Anybody have questions about the review problems? Like we did a couple review problems the other day. Where are they? Down here. Okay. Anybody have other questions about the review problems?
I do.
Mm-hmm.
So for question 9, when asked what the Java object will look like in heap, I'm not sure how that would look like.
Okay, so let's see. Okay, so here's the code. Okay, now, okay, I know what to do. Let's see. Now, this one specifically says, well, this one has color in it, so that means we should use renderer 5. Let me download the renderer, and we'll use the code of the renderer to see how to think about that. Now, first, let me remind you of something that okay. In other classes, I've used the Java visualizer for Java. Now we can't use it in the graphics class because the Java visualizer can't make use of other people's code. Yeah, so you can only use what's standard Java. But here's what I mean by memory diagrams. Suppose I do string s equal HEL, or if I do something like java.awt.color equals new java.awt.color, let's see, dot red. Okay, I just created two objects. Okay. Oh, I didn't give this a variable. Okay. Yeah. Now, the Java visualizer is good at drawing pictures, and this is the idea of what I want you to do. I want you to be able to draw a picture. Whoops. Let me go back and change something. Okay, there's a memory diagram over here. Stack, heap. I've got a variable. See, I've got a string variable in the stack and a color variable in the stack. And I've got a string object in the heap. And I've got a color object in the heap. And this is a memory diagram. The string variable points at the color object, or the string reference variable points at the string object. The color reference variable points at the color object. Okay, so that's how you should think about programming. You know, you have reference variables pointing at objects. The reference variables are in the stack. See, this is a stack frame, and this is the object heap. The object heap over here. Okay, and so now I want you to think of pictures like this when you look at code like this. Okay, so let's go through this code one line at a time. So like that line is just like, essentially it's the same thing as this line. See, what does this line do? It creates a reference variable in the stack, creates an object in the heap, and it makes the reference variable point to the object. This line of code creates a model reference variable called M in the stack, creates a model object in the heap, and makes the reference variable point to the object. Okay, new creates an object. So I needed something to draw a picture with. And I still can't, okay, it was Windows accessories. Now I remember now. I still can't search. So, my Windows machine probably needs to be rebooted. So Windows accessories, paint. Okay, so yeah, if I try to mimic what the Java visualizer does, that first line of code, okay, that first line of code says there's a, whoop, I want a little box. Reference variable with the name M, that's a reference to it's a model. You know, the type of the variable is model, the name of the variable is M, and it's a reference variable. And then it's going to point at it's going to point over here at a model object. Okay, so now I've got a model object in the heap. So this is a model object. This is a model reference variable. That's a model object. And the reference variable points at the object. And I can even put a little arrow in there. See? Okay, the reference variable points at the object. Okay, there's an arrow. Okay, what's in the model then? Okay, see, now I want to open this in code. This is why I downloaded the code. So now go to the renderer, go to the scene class. There's the model class. What's in a model object? What's in here? Well, the model object holds a reference variable to a list object, another reference variable to a reference variable to a list object, another reference variable to a list object, and another reference variable to a list object, a reference variable to a string object, and then a primitive and a primitive. So we've got reference variables to 4 more objects. Okay, so I can go over here in my picture and say, okay, in the model, there are 4 more reference variables. So I'm going to try to do this really drawing it. If you're drawing it freehand, you can do this kind of quickly, but there's 4 reference variables in here. 3 lists and 1 string. Okay, so there's 4 reference variables. Okay, and now I'm going to create a string object out here. There's a string object. So that's an object of type string. Let's see, here will be a list object, another list object, and another list object. Okay, and I know that because I read the code. There's a reference to a list, a reference to a list, a reference to a list, and a reference to a string. And then here in constructor, you can see new list. So I'm creating an object. New list, I'm creating an object. New list, I'm creating an object, and I'm creating an empty string. So I'm instantiating 4 objects. See, 1, 2, 3 new, and strings don't require you to say new. String objects Java gives you a shorthand for string objects. You don't have to say new. You can say new if you want. You can actually say new string. There's a constructor, not many people use it. There is a constructor that looks like that actually, it just does the exact same thing. So if I want to, I can say new string there. Okay, so then I can say, I'll just put the types here. This one's a string object. This one's a list object. This one's another list object. And this one's another list object. Now notice I'm now up to 5 objects. Okay, I'm up to 5 objects. And this guy points to there. Make it that one. I'll make this one point to there. I'll make this one point to there. And I'll make this one point to there. See, they're reference variables. Okay, see, remember, that's a reference variable pointing at a new object. The reference variables in the object I'm building, the reference variables in the model, and it's pointing at some other object in the heap. Okay, so now I've got 5 objects in the heap so far. I got a reference variable in the stack and 5 objects in the heap. This object holds 4 reference variables to point to these other 4 objects. Okay, now the string I'm done with. Strings don't hold anything, but these lists hold things. So now I go back to my other code. I go back to the code we started with, and I see, oh, I create 3 vertex objects and put references into them in one of the lists. So this is adding to the vertex list 3 vertex objects. So I called new 3 times here. So I need, see, I'll make this the vertex list. So I'll give this guy 3 objects below him. So I'll put a vertex object, a vertex object, and a vertex object. Okay. Now that list holds 3 references. If I want, I can put 3 references in there. There's a reference to 1. There's another reference variable. Okay, these are reference variables. So the list holds reference variables, and the reference variables point at the objects. So now over here, I would say that one points to that object. That one points to this object. And this one points to this object. And I'll just put over here a comment that these are all vertex objects. So all 3 of these are vertex objects. Now, what's in those? Go back to the source code. Look up vertex. Okay, so the vertex list is a list object, and the list object is an array of vertices. It's an array of vertices. What's in a vertex? And we reach a dead end because what's in a vertex are primitives. Okay, so our diagram reaches a dead end here. We've got 3 primitives in here, 3 primitives in here, and 3 primitives in here. Just like the string ends with essentially just the string data, these guys end with the primitive data. Okay, so we're up to this picture so far. Okay, now let's make this one the color list. Okay, so actually what I can do here to make the picture a little bit clearer is I would annotate this. This is a list of vertex, right? This one I'll make this one a list of color, okay? And this one is, so you can use the Java, use the generic notation to explain what this is. This is a list of line segments. Okay, that's a list of line segments. Okay, so list of color, list of line segment. They're all 3 list objects, but they have a type to them. List of vertex, list of color, list of line segment. Okay, this one's the list of color. All right, now go back to my original code. Where is my original code? Okay, I put 3 color objects in there. Now they're copies of the same object, but there actually is 3 color objects. So I'm adding to the color list references to 3 color objects. So I can go over here and put 3 more objects in my picture because the color list is going to point to 3 objects. So I'll go up here. I'll put a little, here's a color object. Here's a color object. Here's a color object. So I'll make all these 3 color objects. So all of these are color objects. They're over here. Then the color list holds 3 reference variables to the 3 objects. So if I want, I'd be real careful. I would say there's 3 reference variables in here. Because I'm adding 3 items to the list, I'm adding 3 reference variables to the list to hold those items. Notice that the objects don't sit in objects. Objects never sit inside of objects. Okay. In Java, the only thing that sits inside of objects are primitives and reference variables. Now, what about C++?
C++, I'm guessing it does.
Well, it's a little bit trickier than that. C++ is everyone's favorite complex language. So what do you think the answer would be?
Sometimes.
Sometimes what?
Sometimes it does, sometimes it doesn't.
Yeah, sometimes the objects are in the object, sometimes the objects hold references or pointers. They're called pointers then. In C++, you actually have control over these things. You can sometimes take this object and actually literally embed it into the object, this object here. The object can hold an object. Like it's like arrays are like that, not in Java, not in Java, but in C++, like you can have an array of color and the array actually holds the color objects. Or an array of color can be actually an array of pointers to color objects. Java doesn't give you a choice. When you have an array of colors, you actually have an array of pointers to colors. You never can have an array of colors in Java. Java simplified things. That's one of the examples of how it simplified things. You cannot put a vertex object inside this list, but in C++ you could. Okay, it's tricky, but you have to know how to do it. But if you wanted the objects to be in there, you could. Now here in Java, you can only put reference variables inside of objects or primitives. You can put primitives or reference variables, and then the objects are always sitting outside in the heap by themselves. So now I would put a pointer to that guy, a pointer to that guy, and a pointer to that guy. Okay, now I'm up to what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm up to 12 objects. Okay. What am I building? What, you notice that, yeah. What is this starting to look like?
Tree.
Yeah,
A
same
tree.
tree.
It's a, yeah, that's what the heap is. The heap, actually, it's not quite a tree. If I was doing a more complicated example, you'd see it's actually a graph of objects, because I could have an object, I could create it where this object points back at that object, and so I could have cycles in here. The heap is a graph of objects, where it's like here, this guy, right now, this guy's acting as the node, the root of a tree of objects, because this is not a complicated example. So this object is acting as the root of a tree of objects. A more complicated example would have a graph of objects. Okay, so I'm just going to keep building this tree up now. So no, now what about the color objects? Do I need to worry about my picture more?
No, color just holds a primitive.
Yeah, they hold 3 ints. Yeah, so I kind of, just like the vertices held 3 doubles, the color objects are going to hold 3 ints. So the picture ends there. Okay, so now let's go back to the lines. So now the line segment. Okay, now I've got 3 line segment objects. So I can, almost done with this picture. There's going to be 3 reference variables in here, because I'm going to add 3 objects to the line segment list. Okay, and I'm going to create 3 line segment objects. So here's a line segment object. Here's a line segment object. Here's a line segment object. Okay, I'll go ahead and give those a label. This one's a line segment object. This one's a line segment object. So I have a list of line segments pointing at line segment objects. Okay, that was pretty poorly done. Okay, but what's in a line segment? Go back to the source code. Now open the line segment source. Oh, it holds 2 more objects. Each line segment holds 2 small arrays. So each line segment holds a reference to a small array and another reference to a small array. So, okay, so I got a little bit more to fill in this picture. Okay, so each line segment holds 2 reference variables. So there's the reference variable for that guy, and there's the reference variable for that guy. Oh, I'm not showing the primitives. Like, does the line segment hold anything? No, so the line segment doesn't hold anything else but the 2 reference variables. Like the model held a few primitives, but the question was, how many objects are there? So there's no point in me putting all the primitives into this picture. So I'm not going to put all the primitives. Like, I won't even put what's in a vertex. But if you wanted to fill it in, each vertex holds 3 doubles. So those would be 3 boxes in there, but they're doubles. They don't point to things. Okay, so over here, each line segment points to 2 new objects. Okay, and then I need an array object here, an array object here that these 2 point at. I need an array object here, an array object here, an array object here, and an array object here. And these are short arrays, so I can actually fill them in. It's an array of just 2 things. See, if you go back to the source code, it's an array of size 2. Okay, now it's an array of primitives. So what does that tell me?
They don't hold any objects.
Yeah, I'm reaching the end of my tree. These are not arrays of objects. I didn't do integer objects, so there's not reference variables in here. There's numbers in here. So this will be the end of my picture. Okay, these objects are the end of my picture. I've actually got all the objects in there now. Okay, so let me just add a few more arrows. Okay, this one points at that. This one points at that. This one points at that. Boy, I'm drawing sloppy arrows. Okay. Now, one thing that it'd be kind of worthwhile doing though is filling in. Here's where I think it would be nice to put in the primitive. Put in some more information. What goes in this array? Okay. This array points at vertices. This array points at colors. Okay. This points at vertices. This points at now it doesn't point at. I shouldn't. This holds the index of some vertex. So like. If I wanted to annotate this a little bit, this one has got, this is the 0 index, and this is the 0, 1, 2 index. So this is in the list, this is index, actually the indices really should be up here, but there isn't any room. That's reference variable 0, that's reference variable 0, reference variable 1, reference variable 2, okay? In here, you put the indices of a vertex. If I go back to my original source code, the first line segment holds 0 and 1. So the first line segment has got a 0 there and a 1 there. The second line segment, now that means that this is using that vertex and that vertex. The second line segment has a 1 and a 2 in it. So the second vertex has a 1 and a 2 here. It's using that vertex and that vertex. And the third line segment has a 2 and a 0. The third line segment has a 2 and a 0. Okay. And then there's 3 color objects. And what this does, you have to read the source code, but what that does is it uses the same, it's using the same vertex index, since there's no mention here of the color. See, I didn't say what color indices to use. If you go look at this line segment constructor, where is it? Oh yeah, see, when the line segment constructor only takes in 2 indices, it uses those 2 indices for the vertices, and it uses them also for the color. See, that constructor calls the constructor that takes in 4 indices, but it just copies this one over here and here. So it's going vertex, vertex, color, color. So what that does is it copies into the color indices the same thing that's in the vertex indices. So this will be 0, 1. This will be 1, 2. Now the problem didn't ask for this information. I'm just doing it because I think it's worth pointing out that that's what goes into these arrays. You get indices into these lists. You don't have pointers. These are not pointers into the, like this does not point at that. This just says use index 0 in that list. Use index 1 in that list. Same way OpenGL does it. OpenGL does it the same way. It has a list of vertices, and then the line segments are not pointers at the vertices. The line segments are indexes into the list of vertices. So I'm essentially copying OpenGL's idea here. So it works real well. So I'm copying OpenGL. Okay, so final answer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 objects. I think I counted right. 20 objects. Okay, there's the whole tree. Oh, no, I actually, one, I forgot some arrows. This guy points at that line segment. This guy points at that line segment. And this one points at that line segment. Okay, so there's the last pointers. Okay, so there's the whole tree. Okay, right?
Okay, thank you very much.
Yeah, and see, now, yeah, it took me a long time because I'm drawing it in a paint program. Yeah, if you're doing this freehand, you can draw it in a minute, but you have to know this. You have to know the structure of the code. Now you may need to go look up in the code. Notice how I basically started from the top. Okay, there's a model object. Now that created this guy. It created those 4 reference variables. Now that constructor actually did what? Now it's real important. That constructor did not construct just that object. That constructor also did what? Go look at the code. The model constructor did what else?
Constructed the 3 lists and the
So
tree.
that one line of code created 4 objects, because that one line of code created this object, but it initialized these, actually created 5 objects, because it initialized all these 4 reference variables. So it created the string object, the list object, the list object, and the list object. Now these would be empty, okay? So there would be no reference variable. It would be an empty list with no reference variables in it, an empty list with no reference variables in it, and an empty list. So the model constructor created, see, there's the symbol for creating an empty list. You're calling the default constructor for a list, and it creates an empty list, okay? You could create it initialized, but not in this case. We don't have anything to initialize it with. We're just creating an empty model, but the empty model does point to the empty list. So you see new, 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 new. So this constructor creates 4 objects: that object, that object, that object, that object, and that object. Okay, then these get created one at a time when you do here, create the vertex object, put a reference to it in the list, create another, and this is all done in one line of code, create this other vertex object, put a reference to it in the list, create this other vertex object. So this line of code created that object, that object, and that object, and tied those reference, and put that reference variable in the list and pointed it at this, put that reference variable in the list and pointed at this, and put that reference variable there and pointed at the list. So that line of code created 3 objects and created 3 reference, but you're not asked how many reference variables there are, you're asked how many objects there are. Okay, so you follow your nose through the code, and you have the source code, so you can look up what's in a vertex, what's in a line segment, what's in a, well, you have to know what's in a color. You don't have the source code for color, but you can look at what is in a vertex, so you know that there's no vertices don't point to more objects. But then you look at what's in a line segment, and you find out, oh yeah, a line segment points at 2 array objects, but their arrays are primitive, so that ends the list, that ends the tree there. Let's see. Let me save the picture. I can put it up on the website. Okay, so now Java Visualizer would do this for us. You can write some pretty complicated code in the Visualizer and get really nice pictures over here, but the Java Visualizer has the disadvantage that it won't work with other people's libraries. So our graphics library, there's no way to load it into the Java Visualizer. So we can't draw this, but it would draw essentially that picture. Like if you write your own linked list code and things like that, the Java Visualizer will show your linked lists and all those kind of things. It will literally draw these fancy pictures for you, showing you all the objects. Okay, but and some debuggers will do this for you also. Like if you open this code, where is it? If you type that code into a Java file and compile and run it, some debuggers will show you that tree structure. It depends on the debugger. Some are better at it than others. Some do a pretty good job of visualizing the stuff in the heap. So some visualizers can come pretty close to drawing this picture for you. Okay? Yeah, it depends on the quality of the debugger. They'll all show you this picture, but they'll show it to you as just a variable model holding 3 reference variables that point at, and they'll give you the address of the objects that the 3 reference variables point at. So every debugger will essentially draw this, but many of them will just draw it as essentially as a text file, a description. Just say this model holds 3 reference variables. This reference variable holds a pointer to, and it'll give you the address of the object it's pointing at. So that's what some debuggers do. Some debuggers actually draw nice pictures like this. JGrasp is an example of a debugger that'll draw pictures like this. I don't know if IntelliJ, if they've gotten that far, if they've got some clever, like JGrasp is an educational debugger or an educational IDE, and it was designed to draw these kind of pictures. Okay, and I don't know if IntelliJ does these things or not. I don't know if anybody's got a plug-in for Eclipse maybe that draws these kind of pictures. There might be by now somebody who's written plugins for IntelliJ or Eclipse that can draw this. Okay, so okay, all right, now so that's how that. But again, that's the kind of picture I'm talking about. Same thing, what the Java visualizer would do. Reference variables pointing at objects. Keep track of this picture here. Okay, all right. What about other problems from the review? Is there another review problem that would be worth doing?
I had one quick question about the orthographic one. Do you want us to show a view where, like, if it was at a -1, and
which problem are you talking about?
To number 8 or something like that, maybe.
I mean, like, when is it preferable to use orthographic?
No,
That's 7.
Yeah, hold on, I would have to look at the packets. But basically, I was just curious if you wanted us to draw it so you could see it in 2 different Z positions, but it's like the exact same size because it doesn't.
Oh, no, I think I know what you, oh, no. I think there's one where I said orthographic just to make it easier.
Right, okay, so you just wanted a picture of it, not necessarily what it would be projected to 10, like from -1Z to -10Z, it would be the same exact size?
Yeah, it'd be the same exact size, so you wouldn't even see the projection. Yeah,
okay.
If something's, if that's why I made that one orthographic, because I didn't want you to have to think about the projection step. When things are in orthographic, what difference does it make if it's in the -10 plane or the -2 plane or the -3 plane? Yeah, they all look alike.
Okay.
Yeah, so that, I forgot which one that was that said use pardon me?
I don't remember the number either.
Yeah, and I remember saying that as just a way to say, don't worry about projection. Because if it's projecting, and if it's in the -4 plane, you have to project it to the -1 plane. So it would, you have to find, if I give you something in the Z equals -4 plane and you're using a perspective projection, you have to project it to the -1 plane. So I remember one where I wanted you to not have to worry about projection, so I said use orthographic.
All right.
And then it was meant to make it easier. And I don't remember which one that.
Just doing. Is it number 9? I think it was the number we were just doing. But thank you. That answers the question.
Oh. Yeah, that's one of them. Yeah, it was number 9. Yeah. Draw the picture. The picture. If it was a perspective project, actually it wouldn't matter because I put these in the -1 plane.
Right.
So if I did say perspective projection, since they're already in the projection plane, you still wouldn't have to worry about it. Okay. Cool. So I can make it. I can eliminate you having to worry about the projection step by either saying use an orthographic projection, or I can put these guys in the projection plane, so there's nothing left to project. Okay.
Okay.
What about other questions about these homework problems?
Can we look at number 10A?
Sure. Okay, that's the projection step. Okay, so we've got this vertex. Okay, so we need those formulas. You'll for the exam, you'll want the formulas that they're in this zip file and they're also in your homework 3 zip file. So let me download the homework 3 zip file. You need the formulas. To do that problem in particular, you need all the formulas for the whole problem. Because that problem is literally use one formula after the other. That's a problem where you're essentially using first formula, second formula, third formula to step through the problem. Okay, so there's the formulas that project from camera coordinates to the view plane. So you start with camera coordinates, x sub c, y sub z, z sub p, and you end up with projected coordinates, which are in the z equals -1 plane. So the main thing is compute the x, the projected x, and the projected y. Notice that the projected x is just negative x over z. Okay, so the projected x is the original x divided by the original c with a minus sign in front. Okay, so go over here to the problem. Let's see, now I'm lost. That's okay. All right. So let me go ahead and do it in a let me do it in a text file. Okay. So I've got here's the vertex. There's the vertex. So you notice how this is what I was saying that, oh, okay. So there's the vertex. So x sub c is 4, y sub c is -3, and z sub c is -6. And the formulas tell us that x sub p is, what was I say? It's x sub c divided by z sub c with a minus sign in front. Okay? Okay? So in our case, that would be what? -4 divided by -6. Okay? So that's what? 4/6. So that's 2/3. So that's, see, 2/3 is what? 0.6666667, wherever you want. Okay, so there's that one. Okay, then x sub, or I'm sorry, y sub p, the projected p value is negative of the camera coordinate, the y camera coordinate divided by the z camera coordinate, which in this case is negative of -3 divided by -6, which what that turns out to be -0.5. Did I do that right? Yeah. Okay.
Yes.
And then z sub c is always -1. Yeah, you're projecting to the z plane. Okay. Okay. So what is the vertex in the view plane that this thing projects to? So we're using the projection formula, the first step. Okay. Then there'd be a clipping step. Then from the projection plane, you go to the pixel plane. And I think that's the next part of that problem. What point in the pixel plane is the projected plane? So this thing doesn't need to be clipped because it's already, it's inside the view rectangle. If you notice, how do I know this? How do I know this doesn't need to be clipped?
They're less than 1 and -1.
Yeah, there. Remember, the view rectangle is between -1 and 1. So this is between -1 and 1, and this is between -1 and 1. So it's inside the view rectangle. It doesn't need to be clipped. Now you couldn't tell that originally. See, that's not inside -1 to 1, but it's way back here at -6. So it's being projected 5 steps forward from -6 to -1. That shrinks it. So it shrinks to being inside the view rectangle. So it shrunk to being inside the view rectangle. Okay, so it doesn't need to be clipped. So the problem, it goes from A to B, it skips over the clipping step. That's in another problem. So in this problem, it's projected to be inside the clipping region, so we can skip the clipping step, and the next step is this formula. Okay, so now you've got these two formulas next. So the next step would be, I don't know if they'll copy and paste, right? Yeah, you want the view plane coordinate. Notice that there's not even a z coordinate. Remember I said earlier that once you've projected, you kind of forget about the z coordinate. You know, the z coordinate never gets used again. If you look down here, the z coordinate doesn't play any role from then on. That's why I was able to make z equals -1 as a trick in one of the render steps. Because after you project to this -1 plane, z doesn't play any role anymore. Okay, so there's the next set of formulas. Let's see. Oh, w divided by 2. I was wondering what that equals sign. Yeah, width divided by 2, h divided by 2. So there's the formulas. That's and that's 0. Notice how, see, that's what I was saying. Notice how when you copy and paste from a PDF document into a text file, things get all messed up. That's why on the exam, I gave you all the stuff as a plain text file also, so that you can copy and paste problems or stuff from the exam easily. Because when you start copying and pasting out of PDF documents, all kinds of funny things happen to formatting. You know, why in the world would that period become a colon? Yeah, notice how 0.5 paste in here as 0:5. You know, a period's a period. How did a period become a colon? Well, you know, there's just endless amounts of problems with formatting and fonts and all kinds of crazy stuff. So that's why I gave you the exam also as a text file to save you that grief. Okay. So there are the formulas for the next step. Okay. Now you can plug in what's x sub p. X sub p is, what was it? 0.66667. Okay. And y sub p is -0.5. And now plug in, you know, and compute, you know, and now you can get an answer for this one, and you can get an answer for this one. And in the problem, it told you what the width and the height are for the, see, this is the width of the viewport, and this is the height of the viewport. Okay, so you get those out of the problem. The problem should tell you what those are. Okay. Okay, so that's part B. Then part C was the next step. Yeah. Then part C would be the next set of formulas that go from the viewport to the pixel plane, to the frame buffer. You know, the next set of formulas are going to go, so you can just copy and paste them. Next set of formula would go, this would be the x coordinate in the frame buffer. See, the formatting is really goofy. What is this? This is supposed to be int dot math dot round. That's x, oh, x sub vp. Oh, -1. See, minus sign is double question mark. -1. That's y sub, and that's math dot round. Okay, so, oh, and that's h minus here. Okay, so once you got your answer here and here, you can plug them in here and here and compute the next step. Okay, so you're just going to work. Yeah, that problem asks you to work your way through the pipeline, starting with camera coordinates to projected coordinates to view plane coordinates to pixel coordinates. See, step your way through the pipeline. The only thing it skips is the clipping stage, because this problem, it projects inside of the clipping window, so it doesn't need to be clipped. There's a different problem that asks you to work with the clipping equations. Okay, right? So see, you can, you know, the formulas are there. You just apply them step by step by step. Just, and that's actually what the renderer does. You know, the renderer is just applying these formulas, you know, step by step by step. Okay. What about another problem? Or is there any question about that one?
I have a question about another problem.
Okay.
Can you explain in number 4? I understand 3 of the coordinate systems, but I don't understand view plane coordinates or pixel plane coordinates.
View plane coordinates and what?
Pixel plane coordinates.
Okay. Okay. let's build the Javadoc and look at that, look at this file here in the job, but it looks better if we build the Javadocs. Because there's a picture in there. Hopefully it can. I mean, that's a real subtle issue in this. And I've been trying for a long time to find a good way to explain this distinction between the view plane and the pixel plane. Okay, and a lot of graphics books struggle with this. Okay, and in some sense, it's not. Remember, I showed you a graphic once. I don't know if I have the. Somebody created once a really elegant graphic. Oh. There. This is the pixel plane. And this is the pixel buff. This is the pixel plane. This is the frame buffer. You know, but this picture doesn't show the image plane. The image plane would be like to the left of this guy. But that's the pixel plane, you know, where you just have these dots that represent pixels.
So the
Okay.
pixel plane is supposed to be like the logical.
Yes.
Yeah.
Yeah. It's the plane of logical pixels instead of the plane of physical pixels. And he calls it vector world, raster world. This guy's he's weird. I think he's got brilliant ideas, and then he kind of mucks up things in the details. Like calling this raster world is really weird, and calling this vector world is very weird. It's not. This is the most people call these the logical pixels or the pixel plane, and this is the physical pixels, okay, or the frame buffer. Raster world is kind of a dumb name, and vector world's kind of a dumb name, but the picture is great. Okay, so that's the pixel plane of logical pixels, and so a lot of times we draw it that way, of them superimposed on each other. The dots are the pixel plane, the squares are the logical pixel, or the physical pixels, and a lot of books draw this picture. His brilliant idea was to like separate it like that and say, really, this guy's superimposed on that guy. Okay. Yeah. So it's kind of
what about the view plane?
Now the view plane. The view plane is what you project to the view plane. So the view plane is what you okay. I can't remember. I don't think he's got a good picture of the view plane in that thing of his. A picture of the view plane would be in this rendering folder. I mean, here's kind of the idea. There's the view plane, but this guy, he's also shown it as the pixel plane. So here's somebody say, okay, see, you project to the view plane. There's the view plane. That's what you project to. Now and then he superimposed on it the pixel plane, and the logical pixel plane would be dots inside of there. So in a sense, they're all superimposed on each other. The view plane, the logical pixel plane, the physical pixel plane. You can actually you can merge them all together in one picture. Now he doesn't put the little dots in there. Okay, another example. This plane here is the image plane, the projection plane. You project everything to there. In that projection plane is this projection window that you clip what's outside of it and you keep what's inside of it. So this projection. I call this the image plane. You know, some people call it the projection plane, the image plane. It's this plane that the image is showing up on, that's projected to. See, it's the plane that this thing projects us to. Then you're clipping to this edge. So if something were to go over here and start sliding out of the view volume, it would hit that edge and get clipped. That would be this edge here. Now, in our case, that edge is always at 1, 1, -1, -1. This view rectangle goes from -1 to 1 and from -1 to 1. Okay. Now, that view rectangle has the logical viewport superimposed on it. So the view rectangle has got the logical viewport superimposed on it. That was like over here, kind of this idea here. You think of this and this superimposed on this guy. That's what they're kind of showing here. Everyone's trying to get this idea across. It's kind of, there are really three ideas: view rectangle, logical pixel plane, physical pixels. It's three distinct things, but they can all be kind of superimposed on each other. Here, he's got the physical pixels superimposed on the image plane. This other guy, he's got the logical pixels superimposed on the pixel plane. So he's showing two of them superimposed on each other, and this picture is showing, this one's showing two other ones, you know, the view plane and the raster world. You know, what this would be, what's over here called raster world, and here he's got it superimposed on the image plane. Okay, and in my documentation, I did it as these, you know, so you project to the view plane, okay, then you superimpose on the view plane the logical viewport, which is the pixel plane, and then you superimpose on the pixel plane the frame buffer. Okay, it's hard to draw these. I mean, you know, you kind of in your mind have to. That's why I try to give a lot of pictures. You have to see them as superimposed on each other.
Professor.
Yeah.
Is the view plane supposed to also be logical, or is it something that you can actually physically edit, like a frame buffer?
No, it's logical.
Logical. Okay.
Yeah. That's why we call it, because the frame buffer is a real data structure. So yeah, the frame buffer is a real data structure. The logical pixel plane is logical. It exists in our imagination. So it doesn't even exist as a data structure. This guy doesn't exist as a data structure. It's an idea to help us think about rendering. So it exists as a coordinate system. You transform. We saw the formulas a minute ago, but it's not a data structure like this guy. This guy's a physical data structure. He's in memory. You store things in him. Okay, this is just a thing to help us think about how to go from here to here. We really want to go from the image plane to the frame buffer, and this step in between helps. Okay, so it's a logical step. It's not a physical data structure. It's really just these formulas. It's these formulas here. These formulas are convenient. If I wanted to, I could eliminate step 3, and I could go from step 1 straight to step 4, and it just makes things, it's hard to say. It eliminates a step. Does it make it any easier? It just makes this step way more complicated. And people who do graphics have decided, no, that's not the right way to do it. You should logically break this up into projection, view plane to view. This step is usually called the viewport projection. If you look in graphics textbook, I call it view plane to pixel plane. Most textbooks call it the viewport projection, but that's confusing with the physical viewport because it's a logical viewport. So, but most books, this step is called the viewport transformation. I called it view plane to pixel plane because I thought that's more descriptive of what it's doing. In terms of this guy's dancing, this guy, it's you know, you're projecting to that picture on the left. You're projecting from the image plane. You're projecting from this plane to, you're projecting from this plane to that plane, then from that plane to the frame buffer. And I've not found anyone who's got all three of those steps nicely illustrated, from view plane to pixel plane to frame buffer. Even he kind of, he kind of blurs what comes before the pixel plane. If you go back and, to his steps, yeah, he's got the order of it mixed up. He does have the projection steps somewhere in here, but he's got, instead of, there it is. Here's where he's going to project. But see, he didn't put the image plane in there. The image plane's sitting there in front of the camera. And it's confusing because at first I thought he meant this to be the image plane, but that's just he calls that a background plane. So this plane here is not the image plane, though it looks a lot like it. The image plane would be, perpendicular to the camera. And here's where he's projecting to the image plane. Okay. So it's kind of neat, and see now there's the image. See, there's the axes of the image plane. See there and there, he's showing you the axis of the image plane, but he doesn't really do a great job of explaining it here. And then, okay, now what's this guy? Now where did he step from? Image plane to?
Physical pixels.
Yeah, physical pixels. Yeah. So now he's kind of and notice view space to screen space. See, the view plane to the physical pixels. So there's his kind of. Now again, I mean, I don't think he did a great job here. I mean, it's the idea is there. There's the axes of the image plane, though he didn't tell you that. And that's what he means by view space. And then now view space to screen space. There's the physical pixels laid on top of the image plane. Okay? Everybody's trying to explain, oh no, then now here, there's the image plane sitting in front of the camera. See, now see this plane back here, just ignore it. This is the image plane with the pixel plane superimposed on it, and he's projecting from the world onto this thing here. Okay? So everybody's trying to get this idea across, and everyone's trying to come up with pictures. It's pretty tricky. It's a pretty subtle thing. You'll find it in every graphics book. Everyone's bending over backwards to try to get these ideas across. And he's got them in the wrong order. So here, notice he's got the projection way after the rasterization. If you want to do it in the logical order, you project before you rasterize. That's one of the things that bugs me is they confuse the heck out of the order of these things. You should do them in their logical order. If you want people to understand it, there's the logical order. You project, you clip, you transform to the pixel plane, then you transform to the pixels, the physical pixels. That's the order of the renderer. Every renderer does it in this order, but everybody and their brother describes it in some other order. So their description, and this is one of the things that bugs me about these books, they do the description. Some books will do the projection first, and then they'll talk about the rasterization, then they'll go back and talk about clipping, and then they'll talk about something else. They could really, or they'll talk about clipping first, and then they'll talk about projection second, and then they'll talk about the physical and logical pixels third. I think you should just think it in the right order. Projection, clip, view plane. In the problem we just did, we skipped the clipping because we were already in the view rectangle. If you're in the view rectangle, if you land in the view rectangle, you don't have to clip. You clip when you stick out of the view rectangle. So after you project to the view plane, if you stick out, you clip. Okay, so assuming that you're inside here, then you transform to the logical pixel plane, and then you could figure out where you are in the physical pixels. Okay, and this Making WebGL Dance video or website is kind of neat. He's got a lot of interesting ideas here. he's got a lot of interesting ideas. Here he's talking about anti-aliasing. So he's got the order really blurred in here. So now all of a sudden he's going from rasterization to talk about anti-aliasing. Okay. See that, and then from anti-aliasing, see he's got the shaded, some of the pixels are black and some of the pixels have different shades of gray. That's what we meant. See, the anti-aliasing shades pixels, not makes them white or black, but gives them various shading. So he's doing anti-aliasing here. And then after he does anti-aliasing, he does the next topic we're going to talk about after the exam. We're going to start talking about the linear algebra. So then he jumps to the linear algebra, which is what we're going to talk about next. And then after he talks about the linear algebra, then he goes back and starts talking about projection. See, now here he's talking about projection. So he's got the order really funny. He's got, I think he's got things in a goofy order, but he's got great pictures. Okay. So that helped. That's yeah. It's a good question because it's a where was the question? No, I lost where the question was. Yeah. Camera coordinates are three-dimensional coordinate system relative to the camera, which sits at the origin looking down the negative z-axis. The view plane coordinates are coordinates in the plane z equals -1. Now, you can think of them as 3D, but at the same time, it's really just a plane because all of the view plane has z equals -1. So some people will say it's a two-dimensional coordinate system, and some people say it's a three-dimensional coordinate system. You can quibble over that. If you say it's a three-dimensional coordinate system, the z coordinate has to be -1. Okay, so some people would like this is a three-dimensional coordinate system. A lot of people would say this one's a two-dimensional coordinate system with z equals -1. The pixel plane is a two-dimensional coordinate system. It's this two-dimensional coordinate system of the logical pixels. So it's that plane of the dots that represent the physical pixels. So it's the plane. Now, it's this plane. It's not 2D. This plane here is 2D, but it's got z equals -1. Here I wrote. I could have put the z coordinate because it's sitting in 3D space with z equals -1. But this one's logical. It's not even sitting anywhere. This one we think of as a two-dimensional space of the logical pixels. Okay, yeah, it represents the center. Each logical pixel is thought of as the center of a physical pixel. Okay, and then the viewport coordinates are the coordinates of the region of the frame buffer that's just the viewport. So the 0, 0 is the upper left-hand corner of the viewport. Then the frame buffer coordinates are pixel coordinates, where 0, 0 is the upper left-hand corner of the frame buffer. Okay. Yeah. So this has upper left-hand. This is coordinates relative to the upper left-hand corner of the viewport. This is coordinates relative in the frame buffer relative to the upper left-hand corner of the frame buffer. So if you go back to this picture, this is supposed to be a viewport in the frame buffer. So the frame buffer would be a bigger rectangle like this. It'd be a bigger rectangle around the viewport sits inside of the frame buffer. So this 0, 0 coordinate is that upper left-hand corner of the viewport, but it's some other pixel. It's got some other coordinate in the frame buffer. It's got some, because the frame buffer would have its 0, 0 up here maybe. Up here would be the upper left-hand corner of the frame buffer. So the viewport sits inside of the frame buffer. Okay. So this step here is tough one. View plane, pixel plane. It's a tricky one. That's what lots of graphics textbooks work real hard to try to explain. Okay. What about any last question? Because it's gone over. Actually, the exam is available at this point. Anybody got a last question before we quit? Okay. Boy, I got so many windows open. Get lost in them. This is what you need 2 monitors for. I don't think Zoom can handle yeah, I don't think Zoom can do that. Okay.
I have one tiny question.
Sure.
Can you just really quickly, without going into like much detail, can you quickly just like skim over each of the what's it called, the functions, the formulas that we'll be using, and just in a few words describing what they're for?
I mean, from the formula sheet?
Yeah.
Well, no, projection, clipping, view plane to pixel plane to pixel transformation. Yeah, I don't know. Yeah.
Where do you find this again? Where do you find these?
Oh, that was with homework 3.
Homework. Okay.
Yeah, you needed those formulas to do homework 3 because you had to go backwards. In homework 3, you had to start with X and Y and work your way back to XP, YP.
Okay.
See, homework 3 is where you had to go backward. That's why I gave you homework 3. I figure the most brutal way to learn these formulas is to have to reverse them. And you have to do that all the time in computer graphics. It's not an unusual thing to have to do. You know where somebody clicked on a mouse. When people click on a mouse, they give you these coordinates. These are pixel coordinates. And this is called picking. If you Google the phrase picking, graphics picking, that's what this is what it's called. Somebody picks a pixel and you got to figure out where in your scene were they clicking. You're going backwards. Okay. So it's called picking. Okay. But that's, that's the formulas. It was part of homework 3 because that's where you really needed to use them. Projection, which is its own pipeline stage. Clipping, which is a pipeline stage. This is not a pipeline stage. This is built into the rasterizer. So this is just 2 formulas in the rasterizer. Same with this. These are just 2 formulas in the rasterizer. So these are just buried in the rasterizer. They don't show up as separate stages of the pipeline. Okay. Any last questions?
I have a question.
Yeah. Mm-hmm.
So this is really minor, but I see in the formula sheet for the formulas on number 3, you list the subscript as VP. Is that viewport?
Yeah. Viewplane.
Because in the code, it looks in the code you say PP in the code.
Let's see. This is projected vertex. This is the it's not the view plane. See, this could have been called view plane here because you're projecting to the view plane, and this would be more likely PP for pixel plane coordinate. And did I use different subscripts in the code? Probably. Maybe I chose. Yeah, maybe I should go back and change it. Not in the code, change it in here. Let's see. Let me look real quick. So that would be in the pipeline package, in the
rasterize.
Yeah. So okay. Oh, viewport. Yeah. Oh, yeah, you're right. So I called the VP for viewport. The other one, viewport. So viewport is the same thing as the pixel plane. I'm as sloppy as everyone else. We've got 15 names for everything. So
yeah,
viewport,
that's what makes it a little hard to understand.
Welcome to the real world. Yeah. We call them overloaded terms, and it's just it's so easy to fall into that trap of you use one term in one place and use it. Yeah, viewport is another word for logical pixel plane. Yeah, that's why I told you that people call it the viewport transformation. Remember I mentioned that formula sheet. This is often called the viewport transformation in most graphics books. So I was kind of falling into that habit and calling them, yeah, the viewport coordinates. I probably should go back through and make sure I'm cleaning up the terminology. I've been trying to make sure the terminology was more or less uniform. But on the other hand, if you go look in anybody else's documentation, if you go read OpenGL, you go read WebGL, you go read 3GAS, the words are all over the place. Yeah, and you got to kind of get used to the fact that everyone's going to have a different word for the same thing. So you have to like match them up, like you're doing. You have to match up what one word is in one document with the same word in a different document. You know, different words, same meaning. So you're just kind of stuck doing that all the time as a programmer. You know, trying to say, well, what this guy calls X, this other guy's calling Z. Yeah, so you just have to do that all the time. Yeah, and you kind of wish people wouldn't do it, but they do. Okay, so yeah, so I'm probably being a little bit inconsistent between over here and over here. Next year I'll fix that. I promise. Next year. Okay. Meanwhile, yeah, match things up. Yeah, get things matched up in your mind. That's a good way to do it. Okay, so we'll quit here. We've run over. If, like I said, if you have questions about the exam, send me an email. I have class this afternoon, so I may not be able to get to the emails for a little while. But if you have questions, go ahead and send me an email. And
Will this today's lecture be on YouTube?
oh yeah, sure.
Okay.
Yeah, it'll get up there pretty soon.
Okay.
Okay. All right. So I'll go ahead, and I have to find the button to click on to leave. I've got so many things open now, I'm lost. Let's see. Oh, here we go. Found my stop sharing button. Okay, so oh, and have a nice weekend. So we'll meet again on next Tuesday. Have a nice weekend. Bye.
Oh, crap.
Yeah.
Do we get partial points?
Of course. Yeah.
Okay, nice.
It's like any other test. Yeah.
Okay,
Sure.
just one.
Yeah. It's like any other test. It's not true false. It's not an exam of true false and multiple choice questions. Yeah. So yeah. Yeah. It depends on what kind of mood I'm in, but yeah, they will be graded giving partial credit.
All right.
Okay. All right. Bye bye.